as I said previously, I apologize for the copy quality on these notes. At the very top is what you see on the screen, and if I enlarge it, you might be able to see what the properties are saying. If you want to make a note on those notes where I got this from, this comes straight from page 113 in your text. If maybe when you get home you want to look at that page and see what this should have looked like. But here's the paraphrased version of what you're looking at up there. The addition, subtraction, multiplication, and division properties are all the properties that you use when you are solving an equation. Remember from last year, when you were solving an equation, you were told you can add the same thing to both sides of the equal sign. You can subtract the same thing from both sides of the equal sign. You can multiply the same thing on both sides of the equal sign. You can divide the same thing from both sides of the equal sign. That's all that the addition, subtraction, multiplication, and division properties are telling us. The reflexive, symmetric, and transitive property, hopefully, you were exposed to last year in algebra. We do use them a little bit more by name here in geometry, and sometimes those are a struggle for students to remember which one is which, and the best advice that I can give you is that they go alphabetically. R, S, T, 1, 2, 3. Here's what I mean by that. In the reflexive property, notice I'm only talking about one thing. A number is equal to itself. 2 equals 2. That's it. Symmetric property, notice, says if A equals B and B equals A. You might want to jot down in your notes that the symmetric property is the property that allows us to flip an equation. And sometimes that's necessary in a proof. And the transitive property deals with 3 things. If A equals B and B equals C, then A equals C. You'll frequently hear me say that it's beautiful. It sounds like music. If A equals B and B equals C, then A equals C. You may recall I referenced this property when we talked about the law of syllogism and how if P arrow Q is true and Q arrow R is true, then I can conclude that P arrow R is also true. I can jump the middleman. Sorry, I'm standing in front of you. The substitution property is a lot more cut and dry than the transitive property. Substitution property tells me, for example, if A equals 3, I can take 3 and substitute it in the place of A anywhere I want. A lot of times also, substitution property, maybe you want to jot this down also. Substitution property is sometimes used to condense equations. And maybe that phrase doesn't make a lot of sense right now. When we do an example in which we use it, I hope it becomes more apparent then. Distributive property, of course, you know how to use that. You know how to distribute something. You've dealt with it before when you're solving an equation. However, in somewhere around problem 1 in your notes, you might want to add the statement that the distributive property is the reason why we're allowed to combine like terms. Again, somewhere around problem 1, you might want to add the statement that anytime you're combining like terms, your reason is the distributive property. And some of you may already be thinking, well, why do I need a reason for anything? I know how to combine like terms. I just do it and move on with my life. What we're doing today, however, is kind of starting to dip our toes into the deep and murky waters of proofs. Just out of curiosity, how many of you with older siblings and friends told you, oh, geometry, no, the agony, the proofs? No? None of your friends warned you about proofs?
Matt Anderson did. Until he didn't do any of your homework.
I'm sorry?
Matt Anderson did. Until he didn't do any homework.
Yeah, well, you know, that's...
Yeah, like a D.
Well, that's what happens. All right, so we're going to start off very easy. We're going to start off very algebraic. Okay, so in problem 1, we've seen problems like this before, finding the value of x. What's different between those problems and this one is I don't just want to solve for x. I want to provide a reason for every step in the process of solving for x. Oh, the grimacing, the scowling.
Not some fun.
So much fun. All right, so last chapter, when you saw a diagram and a problem like this, you realized that in order to solve for x, you needed an equation with x. Looking at this diagram, knowing what you know about angles that look like this, can one person please give me an equation that I would use in order to solve for x? What equation could I set up to solve for x? Sir?
2x minus 15 plus x equals 180.
Beautiful, yes. I could set up the equation 2x minus 15 plus x equals 180. And now that she's given us that equation, I would hope that you'd realize, oh yeah, those two angles are adding up to a straight angle, and that makes them supplementary. What you may not remember, which would be understandable, that's why I'm here, refresh your memory, what you may not remember is why, what property, what the name of the property is. The name of the property is the linear pair postulate. And already, I can imagine somewhere in the back of someone's mind, the panic is starting of, oh no, I have to remember the names of all of those properties. And here's the good news and the bad news. On the EOC, remember, this is either a multiple choice or gridded response question. So they can't expect you to write in the name of the property. At worst, you might encounter a fill-in-the-blank proof where they're asking you, multiple choice question, which of the following reasons justifies statement 2? In which case, you would have these to pick out of, and hopefully, one of them would ring the appropriate bell. In this class, however, because this is an honors class, I will, on occasion, throw a from-scratch proof. And yes, expect that you remember the names of the certain properties that we are using. Coming back to the good news, though. The good news is, the more that you do them, the more that we use the properties, the more they end up almost accidentally being committed to memory. Okay, so there's our statement 1, and from there, the rest should be a piece of cake. If this was just an equation that you were asked to solve, what would you do next? What would you do next? How would you solve this equation? You would combine your like terms. So my second statement is 3x minus 15 equals 180. As I said previously, we need to have a reason for every step that we take. I've already told you, anytime you're combining like terms, your reason is distributive property. Once again, if this was just an equation, what would be your next step in solving it? You would add 15 to both sides. And think about what she just said. We are adding something to both sides of the equation. What property allows me to add something to both sides of an equation? The addition property, yes. Finally, again, if this was just an equation that you were asked to solve, you know exactly what that last step is. Go ahead and everybody tell me. That didn't sound like everybody, but yes, your last step is to divide by 3. So x equals 65, and since we're dividing both sides of the equation by 3, what property are we using? The division property. Yes, it is just that easy. Okay, take a moment and try within your group the your turn for problem 2. It will start out a little bit differently. As I said, the your turn for problem 1 starts off a little bit differently. What you had to realize is that you were given a little bit of information on the right-hand side. You were given that ray AB bisects, gentlemen, angle RAN. And so you needed to remember from our vocabulary what happens when an angle gets bisected. So what happens when an angle gets bisected? Yes?
Each side will each other angle will be equal.
It gets cut into 2 equal angles. Yes. So if those 2 angles are equal, it should make sense that those 2 expressions are equal. Meaning your equation becomes, what is it, x equals 2x minus 75?
Negative 75.
It's
Okay.
Oh, sorry.
It's all right. It's Monday for me too. Now, as far as always, you must have a reason. Why did we set these 2 angles equal to each other? Because of that angle bisector. And in general, anytime that's the thought that kind of rolls off your tongue of, well, because it's an angle bisector. A lot of times that means it's the definition of whatever you were just describing, which is, in fact, our reason here. It's the definition of an angle bisector. And again, once you've got your equation, the rest of the process should flow very, very easily. What would be the next step in solving this equation? Subtract what?
2x.
Sure, let's subtract 2x from both sides, giving us negative x equals negative 75. And since we subtracted something from both sides, that's the subtraction property. What next? Haley?
Don't you have to divide it by -1?
Absolutely. So when we divide both sides by -1, we find that x is 75. And since we used the division property, we make sure to indicate that as our reason. In problem 2, coming to the back of our notes, in problem 2, you see that they are asking us for which property is being illustrated there, or what property allows us to go from statement 1 to statement 2. Before I go on to those, I do want to mention that little blip that's above problem 2, the reflexive, symmetric, and transitive properties again, but this time notice they're not talking about equal signs there. They're talking about figures being congruent. So angle A congruent to angle A is the reflexive property. Again, symmetric property allows us to flip around a congruent statement. And then the transitive property allows us to say, for example, if angle X is congruent to angle Y and angle Y is congruent to angle Z, then angle X is congruent to angle Z. So in part A, what property do you see being used here? One thing you might ask yourself is, what happened to the first equation to get us to the second equation? Sometimes that helps. So what happened to the first equation to get us to the second equation? Subtraction, yes. How about part B? What property is being illustrated there? Rs equals St and St equals Tu, why am I allowed to conclude that Rs equals Tu? Transitive property, yes. Part C, frequently the most misdiagnosed property. It is the symmetric property. A lot of times students will want to say reflexive. It's not reflexive. Reflexive is the exact same thing on both sides of the equal sign. This is symmetric. And now finally at problem 3, you see the fun really beginning. Our first real, true geometric proof. Contain your enthusiasm.
What?
Don't everybody jump up and do cartwheels at once.
What happened?
It's okay. Our first real geometric proof. When we do traditional proofs in this class, frequently we use the 2-column format. When we are using 2 columns to do our proof, just like what we did before with the algebra proofs, but I like to label our proofs with statements and reasons. So 2 columns. Almost invariably, about 99.9% of the time, when you are doing geometric proofs in this class, you will start those proofs with the given. Notice in this proof, we are given that AC, the length of AC equals the length of BD. And our reason for that is just, it's what was given to us. So in this diagram, in this proof, we're given that AC equals BD. And somehow, some way, we need to move and shake things so that eventually AB equal to CD drops out of the clear blue sky and into our lap. Think about how we're going to get there. We're told that AC equals BD. Look at segment AC. Do you see that it's made up of 2 smaller parts? What parts make up segment AC? Haley?
A, B, and then BC.
Yes, so we could say that AB plus BC equals AC. And we've dealt with this before. Again, it was a property we haven't used by name in a while. So, of course, let me refresh your memory on that. The name of the property was segment addition postulate. Okay, so we said something using segment addition postulate regarding one of the segments we were told about, segment AC. Can someone give me a comparable equation for BD? Yes? That's exactly it. BC plus CD equals BD. And since I'm using the same reason and the equation looks comparable to it, I can just throw it in to statement 2 along with that previous equation. I don't need to make a whole other statement. And now this is where the real brain stretching starts. Look at the 2 equations in statement 2 and look at how they connect to statement 1. Any thoughts? Ooh, Haley.
The BC's in both are the same, so you can just drop it because it's.
Well, I will eventually, but they have to be in the same equation for me to be able to do that. So she's kind of leading us to where we're going to go. Eventually, I'm going to have an equation with a BC on both sides that I want to just drop off, but we're not there yet. Maddie, do you have a thought?
They both equal the.
Okay, so I think what Maddie's saying by they equal the thing is that this
Yeah. There you go.
correlates to this.
Yeah.
So how can I condense these equations, Mariah? Well,
Or
AB plus BC,
equal.
yes, that's it. What she said was AB plus BC equals BC plus CD. let me put it another way so that maybe you see the connection that she made. Notice that the two equations in statement 2, their right sides are equal. If the right sides of the equations are equal, doesn't it make sense that the left sides should be equal also? And now look at where we are. Look at where we're trying to go, Haley.
Would you have to combine like terms? Like,
But I don't have like terms.
no, like not
I
like
think
that,
you're-
but like the no. I can't think of how to say it. The BCs. You
Okay, so you want to get rid of these BCs. This is just an equation where the BCs are being added on both sides, and she's saying I want to get rid of them. How can I mathematically get rid of the BCs in this equation? I can subtract them away, yes. So finally, AB equals CD because of the subtraction property. How dare I? I never gave you a reason for statement 3.
Oh no.
Oh no! Any thoughts on what that reason would be? Gave a couple of hints here and there. What Mariah did was condense.
Subtraction.
Not subtraction. Substitution, yes.
Just offer one problem.
Mm-hmm.
It's not even a big problem.
Mm-hmm.
This is what I never did in homework.
Yeah.
And that's it. We've completed our first geometric
Wow.
proof.
Too
Woo!
much work
I know.
for one problem.
Oh, let me show you the proof I did in college that took 3 pages. I think you'll be all right.
This is what